Yeah, thank you for the introduction. And yeah, in fact, I will talk more general on relativistic effects, but most importantly, the spin-orbit coupling and how we model them with the Fluor code, something we will do also this afternoon. And I thought I will start a little bit with the basics, the Dirac equation and the Pauli equation, and how this spin-orbit coupling arises from there, and show you a little bit the phenomenology about the relativistic effects, first in non-magnetic solids, something we will not do in the hands-on, but you should be aware of that, and then focus on the magnetic systems, what Daniel had already pointed out. Antisymmetric exchange or Chaldinsky-Maria interaction comes from spin-orbit coupling, and the magnetic anisotropy comes from that. Now, you've seen in the last talk that also in a non-relativistic theory you get magnetism, but actually the way how this spin enters the non-relativistic equations is rather ad hoc. If you look at the Schrödinger equation, this is Erwin Schrödinger here, then yeah, he derived his equation from a classical Hamiltonian with kinetic and potential energy. He did these canonical substitutions, and then you come to a wave equation, and you can interpret these wave functions as a probability density and a current density, but all this doesn't contain any spin labels so far. And then you introduce the spin rather ad hoc. You say that this electron has a spin. This is a good quantum number, which in this non-relativistic theory is okay. And then you suddenly come up with exchange interactions, and then you get your system magnetic, and you can order it ferromagnetic or anti-ferromagnetic. This you can all get out of this theory with this additional quantum number. So you can calculate, for example, something non-collinear. Here I show manganese with tin, which is a Kagome lattice of manganese atoms where the magnetization likes to orient 120 degrees with respect to each other in the individual atoms here. So this comes out from a calculation without spin-orbit coupling, such a magnetization density, but in principle I'm still free to rotate this whole magnetization density by a global spin rotation in space without changing the total energy. And for example, I plotted here 4 different possible magnetic states that could be realized in this manganese routine, which differ basically by the sense of rotation of the magnetization. If you go around clockwise from atom to atom, then the magnetization might rotate clockwise or anti-clockwise, and the global spin direction might be horizontal or vertical, and all these things you cannot distinguish in a non-relativistic theory here. But if you want to find out which of these variants, A, B, C, D, come in nature as a ground state, then you have to include the spin-orbit coupling, and then you find, if you do the DFT calculation, that C is the winner, and this has the lowest energy ground state, followed by D, and A and B are about 5 millielectron volt of in energy. And yeah, to make these distinctions, we now need a theory where we can describe also the spin-orbit coupling in the system. And if we want to do that, then we need to go from a non-relativistic to a relativistic theory, and this is what Dirac found out, that if you want to make a wave function theory that corresponds to this classical Hamiltonian, which is relativistic here, with the same substitutions that we had before, then you come to differential equation which is now first order, but for the wave function, and in addition you have to introduce these matrices alpha and beta, so that if you square then this Hamiltonian, you get back to the classical Hamiltonian, and from this you can derive then conditions for your alpha and beta matrices, so that the correct classical limit is obtained. And these matrices alpha and beta, they are not difficult to find. In a two-dimensional world, they are just the Pauli matrices, which you probably all know. They fulfill exactly these conditions. And in a three-dimensional world, alpha is a 4x4 matrix, which consists of these Pauli matrices, and beta is also a 4x4 matrix, which consists of unit matrices plus and minus here. And the wave function is now also 4-component, of course, and typically written as a large and a small component. And the large and the small component, they have so it's a spin up and spin down part here to make in total a 4-component wave function. And if you want now to see whether the large component is really large and the small really small, here I did a calculation with our code of Bismuth and plotted in the 2s and 2p densities in the muffin tin, and then you see the large components are now given by these full lines here, and the small components, they are not too small. You can see them here by these dashed lines, which are also quite sizable. Of course, bismuth is a heavy atom, therefore you see them rather pronouncedly here. You see they have a different nodal structure, and therefore they're actually quite important for the density which you get out of your calculation. And therefore we also use both components actually when we do calculation with our Fleur code. We construct the density from large and small components. Also for the diagonalization we only use the large component here. Now in principle you can work just with one of these components. If you think that you split the Dirac equation here now with external potential in addition into a system of coupled equations, then you have two equations for large and for small components, and then you can try to insert an expression of the small component up here, and you get an equation for the large component. And then if you do the non-relativistic limit to see whether we get really the same wave function as we obtained from the Schrödinger equation, you can say that the rest mass here is much larger than everything you have from your potential, and then you see this system of coupled equation reduces to something that looks like the Schrödinger equation, but in addition you have now also the vector potential term here appearing. Now in practice we do not take this vector potential in the calculation into account. There are codes where you can do this, but it's a little bit tricky because it introduces additional periodicities of the unit cell if you want to describe the orbital magnetization and all the physics of lambda levels, and so this would be contained here, and this is what we ignore, but we keep the fact that we have a spin up and a spin down part for the large component. Now if we make a little bit more gentle approximation to the Dirac equation and say we keep expansion of 1 over c, all terms up to 1 over c squared, and then you arrive at this equation here, which is also called Pauli equation, which contains now 4 additional terms to the Schrödinger part, which we've just discussed here. And the first is the mass velocity term, which is clearly relativistic origin here. Then we have the Darwin term without classical analogon here. Then we have the spin-orbit coupling term, and this will be the subject of the talk right now. And we have the interaction of the spin with the magnetic field, and this is what Daniel introduced rather ad hoc in his equations in the non-relativistic form. Now, you can take this Hamiltonian and can directly plug it in your DFT formalism, because it's a single particle term. You can just make a DFT with these additional terms here if you make a suitable approximation for this mass velocity term, because here the energy is appearing and here it is appearing, but in practice we use here these linearization energies, which Gregor explained you already yesterday, and then you can use this directly. And in the so-called scalar relativistic approximation, this is what you normally do when you do a Floer calculation. You have, in fact, these two additional terms, which do not couple to the spin. You have them taken into account, and the upper part is basically what you have seen in the last talk, but this you also keep in your equations actually in with the spin-dependent wave function. And this is actually also important that you keep these scalar relativistic terms in here. And to illustrate this, I show you here a calculation of silver and gold bulk. In non-relativistic, scalar relativistic, and scalar relativistic plus spin-orbit coupling approximation. To get to the non-relativistic limit, you just increase the speed of light in the code, and then you switch off, so to say, the scalar relativistic terms. And then you see there is actually not much difference between silver and gold density of states. The deep-band onset is here at 3 eV. In both cases, in gold it's a little bit broader. This is clear, these are 5 d electrons. And if you compare that to the scalar relativistic result, then you see in the scalar relativistic approximation, the gold deep-band starts here at 2, whereas it starts at 3 in silver. And this is actually what makes the difference in color between silver and gold. And this you get out automatically from your calculation. If you then switch on spin-orbit coupling, then you get additional fine structure in the density of states here, more in gold than in silver. But for the color, this is not so important here. Now, after these remarks on the scalar relativistic approximation, let's focus on the spin-orbit term, which I have shown you before. So, in this term of the Pauli equation, has the form of a triple product. You have the spin, you have an electric field cross product with the momentum operator here, and you can rewrite this a little bit, and then you see the spin couples to E cross V, which is nothing else than a magnetic field, because if you move in an electric field, then you see this as a magnetic field, and to this magnetic field the spin couples here, and all the other prefactors here are contained now in the Bohr magneton that you have also seen already in the previous talk. Now, this looks very similar to the spin magnetization or the spin B field term, which we also have, which you can also write as Bohr magneton sigma times B, but in addition you have here a factor 1/2, which is the so-called Thomas factor, which is a kinematic effect which you can derive from the relativistic theory. Now, In the most simple case, if you think you are in an atom, you have a central potential, then the electric field, which is nothing else than the gradient of the potential, is characterized by its direction, which is radially away from the nucleus, and the derivative of the radial part of the potential by the r, and you can collect all this material-dependent stuff here in the spin-orbit coupling constant, and what remains is sigma dot r cross p, and r cross p is nothing else than the angular momentum, and so you see it looks like coupling of a spin to an angular momentum, and this is why this is called a spin-orbit coupling. And you see that this also gives now a source for an orbital momentum in a solid, because it's a term which somehow motivates the system to have a finite orbital momentum and to couple to the spin here. And therefore, without spin-orbit coupling, if you calculate the solid, you don't get an orbital momentum, because the crystal field quenches all this to zero. So the spin and the orbital momentum, they couple anti-parallel, so it's a little bit different than a usual coupling between two orbital momenta. Now, this about the theory. Now let's have a look what this spin-orbit coupling induces in realistic systems. And first, I show you a little bit how it looks in non-magnetic systems. And a simple example, you have seen yesterday the band structure of silicon. And today I show you a band structure of germanium, which is in the periodic table just below silicon. So the band structures, they look very, very similar. And here you have a calculation without spin-orbit coupling, and here with spin-orbit coupling. So in your input file, this means that this sock switch is true and here, and false here. Now you have to put this into quotation marks if you want your input file to work. And then you see the difference. Okay, this looks not very different here, but if you focus on the gamma point around the Fermi level, then you see here you have a threefold degeneracy in the valence band, and here you see that this is split, and you have two-fold degenerate state here and a one-fold degenerate state here. So since these are all p electrons that form these bands here, what you see is nothing else than the typical p1 half with 3/2 splitting which you encounter in an atom. So also in the solid at the gamma point you have a very similar behavior of the bands, and these bands, they are well known to the experimentalists. They have given them extra names in the semiconductor community: heavy hole and light hole bands, and split off band here, and this splitting here is the effect of spin-orbit coupling. Now all these bands are still doubly degenerate, so you have a spin up and a spin down electron sitting in each of these bands, and this comes simply from the fact that we have a structure here which has inversion symmetry. This is again a diamond structure with an inversion center, and we also have time reversal symmetry. The system is non-magnetic, and time reversal symmetry means if I exchange k and minus k and spin up and spin down, then the energy is unchanged, and inversion symmetry allows me to change k and minus k. So in combination, for each state k, the states for spin up and spin down are degenerate, and this is what we have seen. Now if we break inversion symmetry, as is the case for the zinc blende structure, which is similar to diamond but now with two different atoms in the unit cell, and we calculate a compound with zinc blende structure, for example, mercury telluride, and compare this to a compound with diamond structure like alpha tin. So they are approximately similar place elements in the periodic table. The band structure is very similar, but now you see what happens is that here you have a spin splitting of this band between L and gamma, and this spin splitting comes from the breaking of the inversion symmetry and an effect that is called the Ressel-House effect. You can also derive an expression for the Ressel-House effect in Kp theory. Then you see that the splitting goes with k to the third power here. It's complicated, comes from all the symmetries in the crystal, but you simply should be aware if you break inversion symmetry, then spin splittings can appear. Of course, in total, the crystal is non-magnetic, because if you go in one k direction and in the minus k direction, then just the spin up and spin down bands revert here, and in total you keep a non-magnetic crystal. Which also tells you that you have to be a little bit careful if you calculate with spin-orbit coupling. The k-point sampling has to be adjusted such that you sample the plus and minus k sector if you don't have inversion symmetry, but the program normally takes care of that. Now, there are other cases where spin splittings can appear, for example, on a surface. If you think I have an electron that moves on a crystal surface, and then on the crystal surface we also have an electric field because we have a potential gradient, and an electron moving through this electric field sees a B field which is perpendicular to the electric field and the propagation direction, and then the spin will couple to this B field here. And in a free electron model, you can describe this with a simple Hamiltonian, which is called the Rashba Hamiltonian, and this effect is then called the Rashba effect. And you can solve this, and you can observe that in a real crystal, a splitting of the surface states due to this broken inversion symmetry at the surface occurs. For example, in transition metals, copper, silver, gold, we had already before. And there you have surface states which behave almost free electron-like. Maybe you have seen this picture from IBM, where they confined this surface state in a quantum corral. And their dispersion, this is really parabolic. You can observe this in experiment, but if you look now on silver and on gold, then you see on gold you have in addition a splitting of this parabolic surface state, and if you do the calculation you also see the splitting, and you see you split here two different spins, and you also see the antisymmetry when you go to plus minus k. Now, this you can also get out from your simple model Hamiltonian I've shown you before. You can see that the spin direction is then in plane and also tangential to your Fermi contour, and the energies of the spin up and the spin down state is split by a term that is linear in k, and this is the proportionality constant, is then the so-called Rashba constant. So if you do the calculation of a surface with spin-orbit coupling, this is an effect that you will typically see if you switch on this spin-orbit coupling flag in your input file. Another example, here in this antimony telluride surface, you see here a surface state without spin-orbit coupling, and if you switch on the spin-orbit coupling, then it shifts a little bit up, and you see in red and blue that it is spin split again. as you would expect when you turn on the spin-orbit coupling. But you also see, in this case, that something else can happen, that in the band gap that was present without spin-orbit coupling, now new states enter as soon as you turn on the spin-orbit coupling. And, and this comes from a so-called band inversion, which you have between Wells and conduction band here when you turn on the spin-orbit coupling. And this appears if your substance is a so-called topological insulator. And then a Dirac cone of new states appears here at the Fermi level, which you see only with the spin-orbit coupling. And these states here, they have very nice properties. They realize the so-called quantum spin Hall effect, meaning that these states here, they are topologically protected, and they run just at the edges of a sample. So it was first predicted actually for graphene, where you have also band inversions due to spin-orbit coupling, and then you have in graphene, you have edge states which propagate here, and since they are now in different spin channels, so you cannot scatter from one to the other. So if you put some impurity on your surface or on your edge, then the electrons, they can freely travel around this impurity, since there is no additional state where they can scatter to. And after this proposal of Kane and Meili, a lot of people calculated with density functional theory, of course, topological insulators. If you try for graphene, then you will see that the spin-orbit splitting is pretty small. You get something like 25 micro eV splitting if you calculate very carefully. Of course, if you look just at the model Hamiltonian, you don't care. You have a parameter here, delta SO, that gives you a band inversion, and you have your effect. But if you do really the calculation, then you see this is incredibly small, and this you cannot realize in practice. What was realized in practice was this quantum spin Hall effect in mercury telluride, something I've shown you already. If you make quantum wells of mercury telluride, then you can see this quantum spin Hall effect. And also there you have a band inversion that comes from the larger nuclear number of the mercury here. If I compare with the cadmium telluride, the cadmium in the periodic table is above the mercury, and then you see the gamma-6 state is above the Fermi level in mercury telluride. It moved below the Fermi level, and the reason for this is now not the spin-orbit coupling, but actually the Darwin term of the Pauli equation. But spin-orbit coupling is also important, as I told you, to describe the band structure of mercury telluride correctly. So you always need both scalar relativistic and spin-orbit coupling terms to describe these things reasonably. Now, this is all I wanted to tell you about non-magnetic systems. Now, we come to the magnetic systems, and this is what we also will deal with in the afternoon. If you think what kind of interactions are possible between two different spins, say spin I and spin J, then you can think, these two spins are three-component vectors. The coupling can be most generally described by a 3x3 matrix, Jij. And now we can distinguish between the case where I and J is the same, so to say the on-side interactions, and if they are different, the interside interactions, and then we can differentiate between the trace of this matrix, so to say the scalar part of the interaction, and the traceless symmetric and the antisymmetric parts of these interactions. And what Daniel showed you this morning were actually these two interactions. On-site term scalar interaction, this is this famous Stoner I, which he had in his Stoner model, which tells you whether something is magnetic or is non-magnetic. And the interside scalar term, this is this Heisenberg type interaction, which you also get out from a calculation without spin-orbit coupling. So these two things you get without spin-orbit coupling. Here the series tells you it's magnetic and it orders ferro or antiferro or something else. All the other terms which are listed here you get from spin-orbit coupling. The on-site term gives you the magnetic anisotropy, which determines in which direction the magnetization points in space, so up, down, left, right, whatever. And the interside terms, there you have a symmetric and an antisymmetric term. The symmetric one is a kind of dipolar interaction, which is usually rather small, and the antisymmetric part, this is this antisymmetric exchange or Jaruzinski-Moria interaction, which we will discuss a little bit more in detail. So you can think you write this antisymmetric part of the Jij matrix like this, and then you can rewrite this interaction again in the form of a triple product D times Si cross Sj, and this is the form how Jaruzinski actually found the interaction in iron oxides in the 50s. Moria pointed out in the 1960 already that this antisymmetric part is first order in spin-orbit coupling, and this symmetric part here is second order, and therefore in metallic systems we usually find this thing here much smaller and normally ignore in the evaluation of the exchange interactions. Also, it also can make a contribution. But now let's look at the antisymmetric exchange, and you can ask how does it come about. If you think you have two spins, which I call A and B, and you have now some conduction electron that mediates the spin, so it interacts somehow with the spin A, and then it travels from A to B. It interacts with B and travels back to A. Then on the way from A to B, so you have a non-relativistic contribution G0 and a relativistic part, which I write here with this SOC operator in addition. And in the case spin-orbit coupling is 0, your energy is then given by the trace of this product, and if you do this little algebra, then you see that the interaction has basically the form of a constant times the scalar product between spins A and B. And this is the typical Heisenberg type interaction which we have seen already several times. But now, if you have spin-orbit coupling scattering somewhere on the way from A to B, and the spin-orbit coupling operator I've shown you, you can think this is a kind of effective B field times sigma, and now you evaluate this product of these three couplings to the spin, and then you see that this has actually the form of effective B field times SA cross SB. That means exactly this Dzerzhinsky-Maria form, which comes now from the fact that from A to B you have a kind of spin flip scattering on your conduction electron mediating the spin, and this causes then slight deviation from the collinear arrangement, as you can imagine here. So Fert and Levy made a nice model for this Dzerzhinsky-Maria interaction, considering now two spins of let's say light adatoms like iron that are on the surface, and some heavy element, let's say tungsten, which is underneath, and now your electrons, they travel between A and B and the scattering center, and now the Hamiltonian they derived for this exchange process that goes via this atom here below can be described now by a complicated looking Hamiltonian, but you see again in the end you have here the cross product of the spins SA and SB, and here you have a vector in front, and the direction of this vector is given by the scalar product of RA and RB, which are the vectors connecting the tungsten to the two irons. So this D vector is then perpendicular to this plane formed by our three atoms. And now you see also if you would have an additional tungsten atom above, and then you would have another D vector which points exactly in the opposite direction, and this would cancel the D vector which we have here. So if the system is inversion symmetric, this effect is zero. If you have broken inversion symmetry, you will get this Dzerzhinsky-Maria term. Now there are more rules which determine whether this interaction can appear, these so-called Maria rules, but I think that Markus Hoffmann will talk on Friday more on this DM interaction. For us, it's just important to remember that in the non-relativistic case, our exchange interactions between two spins are typically described by this parabolic dependence of the energy, so it doesn't matter whether the angle between the spins is plus phi or minus phi, you have the same energy. But if you turn on spin-orbit coupling, then you get a term which is now linear in this angle phi between the atoms, and you get a counting between the spins A and B, which is preferred with respect to the other. Now, in reality, this can occur in simple magnetic arrangements like domain walls. So I'll show you here a double layer iron on some substrate, and show here a nail type domain wall. You can see that the magnetization rotates now clockwise from domain A to domain B, and then have a second domain wall that rotates again clockwise from B to A, and you can now describe this structure if you plot in the magnetization direction as a function of x coordinate. You see that it changes by 2 pi, so you have a complete winding of your structure. You can assign a topological index to this if you want the winding number. And well, this is one possible solution if you have two domain walls, but you can also imagine something like this, where one domain wall rotates clockwise and one rotates anti-clockwise, and then the magnetization goes to pi and goes back to 0. The topological index is then 0, and now without spin-orbit coupling, this should have the same total energy as in the case with winding number 1, but With spin-orbit coupling, you find out that one of these domain walls does not exist, so it's energetically disfavored, and you have, for a certain system, always domain walls running in the same, with the same rotational sense. And two-dimensional examples of such a behavior would then be fermions, where you also have the Dzerzhinsky-Fourier interaction giving rise to a certain winding number of the magnetic structure. So this is what you can describe easily with spin-orbit coupling. These domain walls, the domain wall width is given by the exchange, and the magnetic anisotropy and the rotational sense is given by this Dzerzhinsky-Fourier interaction. Now the only thing we have not discussed is this last term here, the magnetic anisotropy. I told you this is the on-site relativistic effect, which gives you now orientational dependence of the total energy with the orientation of the magnetic structure. So if you have a ferromagnet which points in z direction, or it points somewhere in the space, it has a different total energy due to this traceless symmetric matrix which describes in the magnetic anisotropy. And you can calculate that in your calculation. If you have, for example, a ferromagnet, you switch spin-orbit coupling through, and you determine the direction of the magnetization by two angles, theta and phi, which give you the polar and the azimuthal angle here. And you calculate the total energy for a certain set of these angles, then for a different set of these angles, and you compare. Then you will find out that you get different total energies, and from this you can reconstruct this magnetic anisotropy here. So phenomenologically, this looks for a system like nickel and iron like this. So this would be the total energy now as a function of different spatial directions. This would be the analytic form. You find then for nickel the lowest total energy is when the magnetization points along the space diagonal, and for iron you find that the lowest total energy you have if the magnetization points perpendicular to the sides of the cubes here. Now, of course, how these shapes look, this depends on the symmetry of your system. If you have an uniaxial system, for example, you have two magnets attached to a rod, and then you rotate this, then this is the most favorable total energy. If you rotate it, the energy increases, decreases again, and the functional dependence would be like this. So you always have to look first what is the symmetry of the system, and then you'll see what kind of constants can appear here, and you can calculate this from total energies directly from the DFT calculation. Now, if you ask what is the electronic origin, why the total energy depends on the direction of the magnetization, you can look at the example like iron here. I have a spin up and spin down states plotted in red and black here in a non-relativistic calculation. And you see spin up cannot interact with spin down, so you have crossings of the bands everywhere. Now, if you turn on spin-orbit coupling, then you see that you get band gap openings in some cases and in others not. And whether you get band gap openings now depends on the relative direction between the magnetization and the orbitals of your crystal. So in two different spatial directions, you get different hybridizations. And then if you think what is the effect on the total energy in second order perturbation theory. You can write it now like this. You can look all states I and j, how do they interact now due to the spin-orbit coupling, do they give rise to a splitting or not. And if one of the states here is occupied and the other is unoccupied, and if the energy difference between these states is small, so if this band gap opening happens now just at the Fermi level, then you will get a large contribution to the magnetic anisotropy. And you also get a contribution to the orbital momentum of the system. And yeah, there are certain symmetry rules where you can then see why these band gap openings occur and why not. So in a very simple example, in a molecule, this is this europium cyclooctatetraene sandwiches here. You have two europium atoms sandwiched in this structure, and if the magnetization is now in the radial direction, then you have two levels in the system which are degenerate. You have one spin here, and if you turn the magnetization then perpendicular, then these two levels are split. You have the spin-orbit coupling, which makes one of the states with a certain angular momentum now more favorable, and then this energy splitting directly translates in a very large magnetic anisotropy energy and also translates in a large orbital momentum. So this is the simple case of a molecule. If you have something more complex, like a solid magnetite, so the standard magnet which you encounter in solid state, you can trace back this effect to similar mechanisms. So you have iron 2+ atoms which are responsible now for the magnetism because they have one spin down electron which sits then in the T2G states of the d electrons. You have an additional Jahn-Teller distortion which splits them off, but it interacts, so to say, the spin direction with the spatial structure of this orbital. And if you dope in an additional electron, if you have, for example, cobalt instead of iron, then you have, again, a doubly degenerate level, like in this europium molecule I've shown you before, and you have a much larger magnetic anisotropy. So in the solid state, of course, this is then broadened to bands, but essentially you can think this is the mechanism how magnetite becomes a strong magnet. In 4F systems, you have then additional effects which come from the special orbital structure of the 4F electrons. In gadolinium, this is rather weak. In terbium, where you have a single spin-up F electron, which is very antisymmetric, you can now think that such a orbital has to be rotated somewhere in the crystal lattice, which also costs a lot of energy, and you also have a large contribution to the magnetic anisotropy here. Okay, let me finally just mention a few effects which also give rise to anisotropies, and which we are actually not considering. You can imagine that a spin also interacts with the orbital momentum of another electron. This is the spin other orbit couplings. You have spin-spin couplings, and you have quadrupole interactions between the electrons. All these effects are higher order. If you want to describe them, you have to go beyond the Dirac equation, and because the Dirac equation is a single particle equation, now you can capture this with the so-called Breit equation. which is actually rather demanding. And normally the most important interactions here you can also capture on a classical level. So the normal dipolar interactions we treat not within DFT, but classically with dipole interactions once we know the magnetic moments of our atoms. So with this disclaimer here, I want to summarize. I hope I could show you a little bit what spin-orbit coupling does in systems with time and space inversion, this P1/2, P3/2 splitting of germanium. In case of just time inversion, this Rashbar and Dresselhaus effects, and then without time inversion, this magnetocrystalline anisotropy, which you get for all magnetic systems. And if you have also broken inversion symmetry in the magnetic systems, then you have this Dzerzhinsky-Morier interaction, which can appear here. And it gives rise to different topological effects, which you can calculate with DFT if you're interested in that. And yeah, with this, I think you're theoretically equipped now to try these calculations in practice in the afternoon. Thank you very much.